There you go. I won't take away your participation. All right. So I think I have spent entirely too long explaining to you how the course is structured and everything. My apologies on doing that. I will try to redeem the day here by saying substantive things. I mean, we have till 4, right? Only 3:30? Yeah, I know. Just messing with you. All right. So first of all, just an introduction. I've already given you the introduction. The next thing is, what is physics? So just make a couple general remarks about that. Your textbook talks about Aristotle and about some of the ancient ideas about physics. When I think of an ancient person who was a physicist, to me, I don't think of Aristotle as much as I think of Archimedes. Because Archimedes was a guy who used math to solve problems and to understand regularities in physical law. Aristotle, I think, was kind of more of a philosopher in some sense. I mean, yeah, that was the basis on which Newton and Galileo, well, first Galileo, of course, then Newton, and others, made progress and invented physics that we'll study. And what is the physics that we'll study? So the physics we're going to study in here is largely what's called classical mechanics, or just mechanics. It's classical because it's not quantum, basically. So classical mechanics is what this course is about. There's two main pieces. The one piece is kinematics, and the other piece is dynamics. So for the most part, we'll be talking about kinematics, at least for the time being. Kinematics is the study of motion, all right? So we pretty much just, we'll describe how things move. We won't explain why, though. We'll just say something's moving, and we'll relate distance and time, velocity, acceleration, these different quantities. That's kinematics. Dynamics, on the other hand, starts to ask the question why things are moving. And that's where Newton's law comes into play. We'll study force and mass, the relation between those things. Yes, sir?
Is quantum the same thing, but on a molecular level?
Yeah, quantum mechanics is something really different. So, yes, there's quantum mechanics so let's see here. The question is, what is the context of the thing we're studying, all right? So if we're talking about, I don't know, baseball, basketball, soccer, pick your favorite sport, daily activities for the most part, these are all, those kinds of motions, they're macroscopic, they're relatively slow, and classical mechanics does a very good job of describing those. Also, the motion of the sun and the earth, like the, earth rotating around the sun, so forth, moon rotating around the earth, these things are described by classical mechanics pretty well because they're relatively slow and they're relatively big. Quantum mechanics has more to do with the microscopic. And there we're talking about things that are so small that no longer the laws of classical mechanics don't really apply there. And there's a different kind of physics that applies. Now that kind of physics is really much more exotic. For example, most of the time in here we're going to be talking about particles. All right, what's a particle? Well, that's a concept. The idea of a particle, a point particle, is that, I'm not a point particle, right? But we'll talk about my position as if I'm at one point. All right. It turns out that if you find my center of mass, you can think of me as if I'm all at that one point, that center of mass, and that's the particle model. All right. In quantum mechanics, we have to think about wave functions and other things. Well, I guess you can take our course in quantum mechanics and learn more about it there. That's a joke. We don't have that course. Yes?
How is it that the laws that govern larger objects don't affect the smaller structures that make the larger objects?
Well, quantum mechanics, I think a theoretical physicist would tell you that quantum mechanics is primary and that classical mechanics is just a special case. Quantum mechanics will reproduce classical mechanics in a certain limit. In the limit, things are very large, and Now, there's more to this story, though. There's also relativity, special relativity over here. And special relativity has to do with when things get, I can't spell, relativity, curses, anyway. So sometimes people just say SR, special relativity, they're safer. Special relativity has to do with when things are going very fast, right? Maybe things still aren't very heavy, not very, very massive, but they're going very fast, like the speed of light. And so essentially what special relativity says, in a nutshell, what special relativity says is that there's a cosmic speed limit, that things can't go faster than the speed of light as it happens. And so Einstein found this special relativity in about 1905, right? But if I'm honest, special relativity actually has to do with what's called electromagnetism. Now, electromagnetism, the study of electricity and magnetism, that is a discovery of the Western world around 1860 or so. I mean, we discovered various aspects of electricity, I don't know, maybe from about 1000 AD to 1700, somewhere in there, Leyden jars, the discovery that different things could be charged by rubbing one thing on another. You've all done this as children, right? You get the balloon, and or maybe you enjoy walking a cart around a dry store and then shocking other people after the charge is built up on the cart after a while. You know what I'm talking about? You can get a really good shock if you got the right kind of humidity. That would be static electricity. But this term, electromagnetism, has to do with electricity and magnetism. Magnetism like a kitchen magnet and so forth, right? Or the magnetic field of the Earth. You notice that's one word. That's because what we learned in about 1860 is that electricity and magnetism were different aspects of one unified thing called electromagnetism. There's an electromagnetic field that involves both the electric field and the magnetic field. It turns out that the mathematics in electromagnetism is already consistent with special relativity. So once we found electromagnetism, special relativity had to follow. It's in the mathematics of electromagnetism. Special relativity, it says really weird stuff about the kind of physics we do in here, but it's actually rather conservative. It's a natural extension of electromagnetism. And then there's more. There is general relativity. What's general relativity? I can't spell. Relativity. Also known as GR. General relativity was discovered also by Einstein in 1916. It took him about 10 years after special relativity to come up with general relativity. General relativity is the physics which best describes very massive things that might be going very fast. General relativity reproduces special relativity in a certain limit. General relativity is it has been experimentally confirmed in a number of different ways. For example, a couple of years ago, there's something called the LIGO experiment, the laser interferometry. I'm guessing the G is gravity. Oh, it seems like observatory, but I could be wrong about that. Anyway, this is a giant experiment which has lasers in vacuum tunnels or something like that, and they were able to detect what are called gravitational waves. So gravitational waves are part of what general relativity predicts. It also predicts that time behaves a little bit differently than special relativity. And in fact, there's a general relativistic correction to your GPS. The GPS on your phones, in a sense, involves general relativity. But generally speaking, general relativity doesn't enter our daily lives that much. For the most part, if I was to say, take this marker and do this, that's mostly classical mechanics, right? You can say that there's an acceleration of minus g going down. I gave it an initial velocity. We'll study the equations which govern that motion in here. That's classical mechanics. That's what we're studying. Next semester, you'll study electromagnetism in here. I might say a few more words about quantum mechanics at the end if there's interest. But this is kind of the big picture. There's a lot more to say about quantum mechanics. Inside here, there's what's called electroweak theory, which combines electromagnetism and weak force. Weak force has to do with radioactive decay. There's also the strong force, which describes how gluons and quarks bind together and then form nuclei. Nucleus and neutrons and protons are built from quarks. This is described by something called quantum chromodynamics. There's a more sophisticated theory of electromagnetism called quantum electrodynamics that was discovered by Feynman, and also a Japanese researcher, I think by the name of Tamanga, also Schwinger, around the World War II. So I mean, there's a lot of physics that we know, but I think it's important for me to give you sort of a general philosophical comment here, which is that all of this being said, none of these things are strictly true all of the time. All right? And so we say that they're laws, but what we really mean is that they're true in a certain approximation, in a certain circumstance. We can expect these things to work out as they do. Now, what I just said is a little bit, perhaps, well, okay, so why do we think, you'd be like, well, where's a place where general relativity doesn't work? Well, that objection it's more a mathematical one, all right? When we study the mathematics of general relativity and quantum mechanics, they're not compatible, all right? And so that's why a lot of theoretical physicists right now are studying, you guys have seen the Big Bang Theory, right? Mm-hmm. So what are the two competing theories of gravity? String theory and, yeah? He gets very upset in this one episode because they can't agree on this, yes. I had not seen much Big Bang Theory, but I happened to see this episode. It was amusing to me how informed this show is on modern theoretical physics. Loop quantum gravity, yeah. So anyway, string theory is, I would say, probably not physics at the moment, but it's, what string theory is the extension of quantum mechanics to solid objects, actually. So the quantum mechanics that we know is for point particles. String theory would be quantum mechanics for extended objects. That's a fantastically hard thing to actually do. And I think it's probably fair to say that physicists and mathematicians will be working on that for the next 100 years, most likely, right? There are no physical predictions so far from string theory. It's just speculation, yeah.
Could you give an example of an extended object?
You're an extended object. I'm an extended object. I mean, something that has this paper, anything that's not a point. I guess the better question is, can you give me an example of a point? Like, what's a mathematical point? But even that's got size, right? You understand? I mean, this, if you can see it, it's not a point. I mean, this is the difference between a mathematical point is just that one isolated location. This, if I could zoom in enough, I could tell you how big it is, right? But you're right. In common language, we say that that's a point, right? But that's an approximation. What we're really saying when that's a point, when we say that that's a point, what we're saying is that the particular size and shape of that doesn't matter to us, and we just want to think about it as something that's right there. That's the idea of a point, or a particle. All right, so I have digressed from your book, obviously. I mean, if you read the book, it just says stuff about, Galileo and the ancient Greeks and stuff, and I thought we should have a talk about what's the big picture of physics right here. I want you to understand that physics is a larger family of ideas. It's all these things, right? But in a nutshell, physics is trying to understand God's creation. This is my words, of course, but it's trying to understand God's creation with precise mathematical laws. I don't think you can take math out of physics. Part of physics is mathematical. That's one of the things that distinguishes physics from other kinds of sciences. There's much more math in physics than, say, biology. Yeah. Mm-hmm?
So, based on what you said,
Yep.
all of the laws of physics apply and then they don't apply all at the same time. And I guess one that I would think of is the CERN Higgs boson particle that doesn't fully add up, which makes sense. But how is it that you can even get a law of physics if you need to prove those laws of physics based on other laws?
Well, laws of physics are much like mathematical theorems, all right? They have sets of assumptions going in, right? So if I'm going to say classical mechanics applies, that means I'm talking about things that are relatively macroscopic, that aren't going close to the speed of light, all right? Also, where electromagnetism doesn't play too big a role. Each one of these laws of, each theory of physics has its own particular point of application. Now it is general, in the sense that, I mean, physics is a very, what's the word I'm looking for here? It's reductive, right? So we try to take many things and describe them in terms of a few basic things. So that's a little bit different than other kinds of science, which tend to be more about just giving a label for something, right? And not trying to, physics is always after trying to explain many things with just one thing, all right? So that's another characteristic of physics, but that's not universally the case. There's also parts of physics which are what you might call phenomenological. A phenomenological part of physics, if you're describing something with phenomenology, what that means is you've got some sort of heuristic picture of what it is. You can't actually derive it from basic principles, but still you can say a lot about it. Much of nuclear physics is like this. You've heard that, have you ever heard of this? That protons are made of quarks, right? Quarks are described by something called quantum chromodynamics, which is chromos for color, and quantum chromodynamics. And so this is a quantum field theory. So in principle, you should be able to find solutions mathematically to this quark math, which produce neutrons and protons as bound states, what are called bound states in quantum mechanics. No one's done this math. As far as I know, this is an open problem. If you could actually produce neutrons and protons as bound states of quarks, if you could work out the mathematics of that, you'd probably get a Nobel Prize or something. It's a big unsolved problem. So you're like, well, if you can't reproduce neutrons and protons mathematically, then why do we believe there are neutrons and protons? Why do we believe neutrons and protons are built from quarks? Well, there's other things. There's these things called quantum numbers, and if you study the quarks, if you say the quarks have certain properties, and then you combine them, well, the neutrons and protons have the properties that should come from building neutrons and protons with those quarks. It doesn't really matter the details here at the moment. The point is there are convincing reasons to think that neutrons and protons are built with quarks, even though we can't describe exactly how that happened. That's kind of an example of phenomenology. There's parts in physics that we don't. There's a lot in physics we don't understand. All right, it's an ongoing project that we don't have complete understanding. That said, in here, not so much. All right, it's cut and dried in here. Like what we're going to do in here, it's done. All right, so let's get to that. I'm sorry, guys. Dimensional analysis. So your questions are very tempting, but I should focus. So I'm not entirely. I'm just going to be behind. Let's face it. As I said, it's a tentative schedule, right? Hey, worst comes to worst, we'll just cut a topic off the end. You guys won't be offended, right? You're like, you're studying for some kind of standardized physics test? I should warn you, I'm not intending to prepare you for such things, right? I had a medical student in here who complained that the physics didn't prepare him for the MCAT or something. Is that something you take, MCAT? Is that right? Yeah. I was like, yeah, that's right. I don't teach to a test. So it's true. Dimensional analysis. So basically the central idea here is you cannot add apples and oranges, I guess, is a way we could say that. Although it's a tired saying, but what I mean by this, let me kind of cross that out, and that's just being silly, is you cannot add quantities with different dimensions. All right? Dimensions. What's a dimension? Now, here, when I say dimension, I'm not talking, we talk about 3D and 2D, those are physical, spatial dimensions, right? This kind of dimension I'm talking about right now is a different thing. Let me tell you. So, little chart here, symbol, name, quantity. So we have A, which is for an ampere. This is electric current. We have K, which is for Kelvin. What's that? Yeah, temperature. We have S, which is for second, which is about how much time I have left. That's time. We have M, and this is unfortunate, guys. M is for meter in here. But what else is M for? Mass. It's true, and there's definitely danger of confusion there. Oh, see, I already did it. I'm not trying to... we spell meter this way because we're not British. I mean, I'm not British. I don't know, mass. Let's see here. kg is kilogram. Oh, come on. Seriously? Really? Look at this. Look at this. This is sad. What should go up here? What is meter? What is the quantity that meter is the unit for? Right, length. All right, I'll get it eventually here. I'm going to stop writing, but the other two you could put here would be candela, which is C-A-N-D-E-L, which is for luminous intensity. All right, that has to do with light, how many photons are coming at you in a given unit area time. And you could also talk about mole, which the chemists like, right? Yes, was that 6.023 times 10 to the 23rd? Why do I still know that? I learned that in chemistry. I would much rather know the birth dates of my children. But I know that stupid number instead. Thank you, chemistry. It's all your fault. All right. Now, I would point out, and again, I can't help but apologize for the lack of content in this lecture. I promise I will tell you many more things about physics next time of a more quantitative nature. This right here is really weird, because here the name actually involves a multiplier. Isn't that weird? What is that kilo for? Right. So this is important that we know about this. What's mega? 10 to the 6th. What's the symbol for that? By the way, this is a K. This is a big M. What's a micro? 10 to the minus 6, right? And we use a mu for that. Not like a cat, but like a Greek letter, mu. What else? What other common multipliers that matter? You'd like to have this many bytes, right? Tera, yes, 10 to the 12. And of course, we also have nano, which is what? 10 to the minus 9. Our symbol for that is N. All right. I'm sure I have missed some. Let's just talk briefly about significant figures. What's the mass of the sun? So you get it, and you set it on a scale, right? And then you read it, right? Make sure your batteries aren't out. And 1.989, huh? I got 1.99. My textbook beat your Google. Not really. Your Google's probably right. But anyway, for problems in here, if you said that the mass of the sun was 2.00 times 10 to the 30th, that's probably good for a lot of problems. That's part of the joy of not using electronic homework in here, is we don't have to quibble over whether it should be 1.99 or 2.00 and whether or not that's going to make your electronic homework, not see a right answer as a right answer, which is just ever so slightly off, right? I can tell. As a general rule, guys, let's agree that you're going to give me answers that have 4 numbers in them. Unless it's like 3. You know what I mean? Like if the answer is 3, fine, 3. You don't have to write 3.000. That's not what I'm saying. I'm saying that, if it's a long, ugly decimal thing, I just need 4 of those. Not 4 decimals, but 4 total. So if you had like 483.62627947, whatever, I just want the 483 point, the first thing. 4 numbers will be enough for me to tell that you did the math or the analysis right. And that is independent of significant figures. That's just for the purpose of me grading. Now, significant figures is a more delicate issue, which we might test on, right? Your question about sig figs?
Yeah, that would be my question.
So this right here would have 3 significant figures, right? That's the convention. I gave the example in lab this morning. If I said 800 miles, how many significant figures? You can't say, right? That could be 800. That could be like 800 miles plus or minus 10 miles, in which case it would have 2 significant figures. If it was 800 miles that we know to within plus or minus an inch, well, that would be many more significant figures. I think we worked out this morning in my lab that if you did 800 miles plus or minus a foot, if you actually convert that foot to a mile, you get 7 significant figures. So the significant figure means that the numbers we've written are true, and the last digit doesn't have to be certain, but it has to be true to within like plus or minus 1 or 2 or 3. The book says 1 or several, so it's like, we're not going to commit to a specific thing, right? I'm not that big on sig figs, guys. I'm much more interested in physical law and so forth. So, all right, well, I think that's all I've got to say about Chapter 1. We will start in Chapter 2 next time, guys. All right? Thanks.
Is it okay?
For a second.